Today, I will talk about Bloch-Optimized Dithered-Ultrasound-Pulse RF for low-field Inhomogeneous-Permanent-Magnet MR imagers. I have no financial interest to disclose. The complex infrastructure needed for high-field MR scanners has relegated this very safe and remarkably revealing clinical tool to high-end hospital care. But for many potential applications of MR, such as point-of-care diagnostics and classroom experimentation, image quality is far less critical than portability and low cost. Emphasizing this has led researchers to focus on low-field MR of the order of tens to hundreds of millitesla, generated using arrays of inexpensive permanent magnets. However, these systems can be quite inhomogeneous in comparison to clinical superconducting magnets and often undergo drifts due to temperature changes. In this talk, I will describe our approach for designing Bloch-optimized, amplitude and frequency modulated MR pulses that leverage ultrasound technology to achieve dramatic cost reductions, while still generating RF needed for the higher B0 inhomogeneity associated with permanent magnet arrays. Ultrasound and low-field MR share a similar range of center frequencies, but thanks to the large portable ultrasound market, there are a number of low-cost integrated circuits for generating ultrasound pulses. For example, we use an 8-channel pulsar from ST Microelectronics to create programmable high-voltage pulses for inhomogeneous permanent magnet MR scanners, as well as receiving low-amplitude signals through its built-in TR switch. Because each channel is driven by 2 digital bits, the chip can be enabled by square wave inputs from an inexpensive Teensy 4.0 microcontroller. The adjustable 600 MHz ARM processor of the Teensy provides dynamic clock scaling and allows for reliable generation of square wave pulses using the command digital write fast. This particular command has reproducible and precise timing, and despite the 3.3 nanosecond constraint between instruction cycles, we can carefully control the RF output to properly excite a bandwidth of frequencies. Amplitude modulation is achieved by adjusting the pulse duty cycle, and frequency modulation through altering the period of these square waves. Through a combination of both amplitude and frequency modulation, we create what we call dithered pulses. For the rest of this talk, I will focus on the optimization of a pulse centered at 8.13 MHz to be used in permanent magnet arrays with B0 around 190 millitesla. Since the microcontroller can only make precise updates every 3.3 nanoseconds, it is not possible to generate exact square wave pulses for all frequencies. Instead, we set up an optimization where 3 amplitude and 3 frequency modulation choices are given for a total of 9 dithered pulse options. And from that, we optimize for proper excitation of the Z-directed magnetization within the bandwidth of our permanent magnets. As other groups have previously demonstrated, broadband and adiabatic MR pulses can be designed through numerical optimization and optimal controls design of the Bloch equation. Because of the limited degrees of freedom of our hardware, we can set up an optimization of excitation and refocusing pulses to satisfy the Bloch equation over a specified bandwidth. Given these limitations and short pulse durations needed when driving at high amplitudes on the ultrasound chip, optimizing a discrete time solution to the Bloch equation can be done within minutes on a CPU using MATLAB's constrained optimization genetic algorithm. The Bloch magnetization vectors at the end of a fixed duration pulse can be pre-computed for various frequencies in the specified bandwidth for all dithered pulse combinations. From the Bloch simulation, we obtain plots here of the X, Y, and Z nuclear magnetization spins for an isochromat at 8.12 MHz over the duration of the optimized pulse. However, for the pulse to optimally flip and align the spins within an inhomogeneous permanent magnet, we need to simulate the spins across a large bandwidth. Here, the MX, Y, and Z components of 3 isochromats over a 100 kHz band are plotted. As shown, the optimizer was able to phase align MX and MY for the isochromats by the end of the pulse, and in the Z direction, the simulated pulse achieved convergence to 0 for a 90-degree flip. Now looking at all of the simulated isochromats across the 100 kHz bandwidth, we can see phase alignment in the X and Y directions, and MZ isochromats that converge to 0. Likewise, we optimize for a refocusing pulse. For the 180-degree refocusing, the simulator optimizes to produce the appropriate flip for initial conditions of either MX or MY equals 1. Once we optimize for the proper magnetizations and flip angles, we obtained a dithered pulse sequence. If we overlay several periods of the optimized pulse, we can see both frequency and amplitude modulation have been applied. Taking the FFT, we obtain the frequency spectrum of our RF pulse, which we use to validate the Teensy generated RF is in agreement with our simulated pulse. We recorded the pulse and its FFT on an oscilloscope. Comparing the measured pulse in blue with the simulation shown in orange, we can see that they are in close agreement in both time and frequency. As highlighted in red, the amplitude of the Fourier transform frequency spectrum varies over the 100 kHz optimized bandwidth. However, to get a better sense of the performance of the pulse, we looked at the magnitude and phase of the XY magnetization vectors versus isochromate frequency at the end of this 90-degree pulse. Zooming into the target optimization bandwidth, we can see that there is nearly constant excitation and small phase variation across the 100 kHz. Likewise, we examined the 180-degree pulse for two initial conditions. The first, shown on the left, being the initial condition of zero phase, where mx equals 1 and my equals 0. The second initial condition was for a rotation about the x-axis for a 90-degree initial phase, where mx equals 0 and my equals 1, as shown on the right. Again, zooming into the highlighted optimization bandwidth, for both initial conditions, the magnitude and phase are quite flat. For the case of zero initial phase, the phase at the end of the pulse is 0, and for the 90-degree initial phase case, it reaches minus 90 degrees. We limited our RF amplitudes to plus or minus 30 volts in this simulation, but with higher drive amplitudes, even flatter magnitude and phase can be achieved. As mentioned earlier, various permanent magnet array topologies for low field MR exist. To test the performance of our RF subsystem, we used the spokes and hub magnet topology as presented at ISMRM in 2019. These magnets were designed to be homogeneous on the order of hundreds of parts per million for an XY slice at the center of the magnet. Our simulation of this magnet shows that in an 8x8 millimeter field of view in the XY plane, the field pattern is radially symmetric and has a bandwidth of 5 kHz. However, the field in the z direction is 10 times more inhomogeneous, with a bandwidth of 50 kHz across the same size slice. We tested the entire signal chain using the dithered pulse, the spokes and hub permanent magnet, and an 8 millimeter diameter test tube filled with water. Here we can see a clear spin echo before and after down converting to baseband, and the frequency spectrum, which shows a bandwidth of about 50 kHz as we expected based on the B0 simulations. Because small changes in geometry can significantly shift the field within a permanent magnet, we aim to see whether the 100 kHz pulse could perform proper excitation and refocusing when the magnet geometry is altered slightly. By increasing the Z separation of the magnet by 50 microns, the center of frequency of the magnet decreases by 20 kHz in simulation. Since the shift in frequency is still within the bandwidth of the optimized pulses, we can see that the resulting spin echo in the time domain for the increased separation distance magnet matches that of the original, while in the frequency domain, the spectrum has been shifted by 20 kHz. We also played the same 90 and 180-degree pulses in other permanent magnet systems. The top row shows a spin echo on a more inhomogeneous spokes and hub magnet with lower center frequency, and the bottom row shows an echo on a tightly shimmed MIT MGH tabletop scanner. Finally, we examined the efficacy of the pulses when different strength gradients were applied to broaden the frequency spectrum. Looking at an 8 millimeter diameter on the tabletop system, we observed the narrowing of the spin echoes in the time domain and broadening of the frequency spectrum as one would expect with increasing gradient strength. Similarly, for a phantom with 2 offset holes, we can see the spectral separation of frequency peaks when larger gradients were applied. And lastly, for a spokes and hub magnet, we introduced a permanent gradient and obtained a spin echo with 100 kHz bandwidth, demonstrating that the spins are being excited within the entire bandwidth of the optimized pulse. With that, I'd like to thank my lab mates, collaborators, and our funding sources, and thank you for your attention. I look forward to answering questions during the live Q&A session.